Our last topic in stats is chapter 12, which is one-way analysis of variance. In this chapter, we're going to examine the idea behind ANOVA. We're going to go ahead and compare several means. We're going to look at the problems associated with comparing several means, and we're going to re-examine the ANOVA F test. So again, this is section 12.1, inference for one-way analysis of variance, and it's May 4th. In our last few chapters, we've had the ability to compare two groups. When we do compare two groups, we've been using T procedures, and the idea behind that is to ask ourselves, is there a difference between the two groups, and is it statistically significant? When we use analysis of variance, this is our statistical method for comparing several means, and we do abbreviate it ANOVA. This chapter looks at one-way ANOVA, and we use this procedure when there's only one way to classify the population of interest. So the category of interest is called a categorical explanatory variable of a factor. And to demonstrate that idea, we have an example. So we would compare the average tread life of 5 specific brands of tires. So the average tread life is our category of interest. We also have a two-way ANOVA, which is chapter 13, and we're not going to get into that this year. But we would use the two-way ANOVA when there's an interest in analyzing the effect of two factors. So not only would we compare the average tread life of our 5 specific brands of tires, but we would also look at the temperature. The idea behind ANOVA is to determine if there are differences among our sample means and if they are statistically significant. So the analysis of variance, or ANOVA, compares the variation due to the different sources within the variation among individuals who should be similar. So our population should be similar or close, but there's going to be differences in each sample that we take. So when we examine the ANOVA test, we'll have several different populations means present. So we'll be looking at how far apart the sample means are from each other and how much variation exists within a sample itself. So if we're comparing two populations, we usually assume that they have equal but unknown standard deviations, and that the sample sizes are also the same of size n. If this is the case, we run our t statistic as follows. Normally, when you assume that the populations are the same, we would subtract the differences, and then of course we would pool because we're assuming that the standard deviations are the same. We can also build off of this and come up with the ANOVA F statistic by simply taking our t statistic and squaring it. And we've seen this in our ANOVA table already. So this is how you would calculate the F statistic. We would still subtract the different population means. We would then divide that by 2 to average it out, but we would use a pooled variance. So when we calculate the F statistic, we have both a numerator and a denominator in that ratio. The numerator will measure the variation between the groups. So they're looking at the difference between their sample means. Are they close together or are they really far apart? The denominator in that ratio will measure the variation within the group. So how much difference are you seeing in the observations in one sample by itself? When we run the ANOVA F statistic, we're testing the null hypothesis that the population means are all equal. And that was why we pooled in the first place. If we have evidence to reject the null hypothesis, we don't just say that the test is over. We actually have to analyze our conclusions and figure out which populations are different and by how much. If each individual sample contains an outlier or any extreme deviations from the normal, we can have invalid results even if we run the procedures correctly. Those extreme deviations from the norm will affect our results. When we reject the null hypothesis and we say that the means are all the same, it's not the same as concluding that the means are different from one another. So when this happens, prior to running the test, we have to come up with our alternative hypothesis. And it's not enough just to say that the means are different. We will actually set up what's called a contrast so that we can examine all of our different results. We're going to stop there for today. There's no homework with this set of notes. If you have any questions about the notes that we've covered today, make sure you contact me so we can clear it up. Have a great day.